Hello, this is Mrs. Schroeder. Welcome back to chemistry. Today we're going to talk about section 3 in chapter 8, how to identify types of reactions. We learned yesterday how to balance them. Today we're going to learn how to classify them. So the question is, why do we want to classify anything? Why do we care? In order to classify them, we have to look at what the products are and what the reactants are. They're classified based on the type of those compounds. Some general types of reactions. These are only 5 that we're going to talk about. There's a lot more than this if you get into organic chemistry and start getting into more complicated chemistries. But for our purposes, we're going to simplify to these 5 types: combustion, synthesis, decomposition, single replacement, and double replacement. The reason this is important is because it allows scientists to understand and predict outcomes of reactions. So we want to be able to predict things. First type is a combustion reaction. Combustion means burning. Anything that burns is a combustion reaction. Anything that burns that has carbon in it. So these are carbon-based molecules reacting in the air, and you see the flames. The product will always be CO2 and H2O. So something else might react with air, but if it doesn't produce carbon dioxide, it's not a combustion reaction. Another clue as a combustion is that heat is given off. Things get very warm. As you know, if you try to touch a fire, you're going to burn yourself. An example of a combustion reaction is when ethanol reacts with oxygen. It forms 2 carbon dioxide and 3 water molecules. Another example, propane. This would be in your gas grill. C3H8 plus 5 oxygen goes to carbon dioxide and water. So you always see these products, and you always see the carbon of some kind in the reactant side. Oxygen is always implied. If it burns in air, it's burning in oxygen because oxygen is in air. The second type is the synthesis reaction. If you're synthesizing something, you're making it, you're putting it together. Same thing in chemistry. If we're synthesizing something, we're putting it together. So we take 2 of something, or it could even be 3 of something, atoms or compounds. We're combining to form 1. Often we like to kind of simplify it. A and B don't stand for any specific chemicals. They're just a general A plus B. A could be anything, B could be anything, and they form a compound. Again, it's not balanced. It's not showing you subscripts or coefficients, just showing you the pattern that we might see. We have 2 on this side and 1 on this side of something. Examples of that: if I take sodium and I react it with chlorine, Cl2, I get sodium chloride. Now notice when it's balanced, we end up getting the 2's for the coefficients and subscripts, and that's okay. But this is just the pattern. Up here is the pattern we're talking about. Another example would be metal oxide. In this case, if you notice, it's not an element. It's actually 2 compounds that are reacting, but you still see 1 compound at the product side. So it's still a synthesis reaction. Decomposition is basically the opposite of synthesis. When you're decomposing something, you're breaking it down. Again, it's 1 thing going to 2 things. So on the reactant side, you see 1. On the product side, you see 2. And again, it is the opposite of synthesis. So oftentimes you'll see a reaction written as a synthesis reaction. You might see it later on another paper written as a decomposition, just flipped. Examples: we can take hydrogen peroxide, H2O2, and break it down into water and oxygen. Okay. No, it didn't break down to the 2 elements. Sometimes it does break down to the elements, H2O and O2. But sometimes we have things that break down into a compound and an element. It's still a decomposition because it's 1 thing on this side and 2 things on the product side. A single displacement reaction, or some books you'll see will call this a replacement instead of a displacement. It means the same thing. It just depends which book or which chemistry terminology you're using. In this case, a single element is reacting with another compound and replacing a single element from the compound. So the pattern we see is A plus BC goes to AB plus C. You always see a single element on both sides. That's what clues us in, because there are two things on the reactant side and two things on the product side, and one of those things is an element on both sides. Okay, a single element by itself. Example of this, aluminum and copper chloride. When they react, we see the aluminum and the copper replacing each other. So aluminum goes into the compound and copper gets kicked off and is over by itself. Single replacement. Single meaning single element. The last type is a double displacement. This is when two compounds form two compounds. Usually when we're talking about these, we're talking about aqueous solutions. So we see two new compounds forming. In order for this to actually have a reaction occur, instead of just being mixing two solutions and still having solutions, if you want a reaction to occur, I have to have a solid precipitate, a gas, or a molecular compound, like water. That's considered a molecular compound. One of those has to form, or else it's simply a mixture. So if you put them together and nothing happens, it's just a mixture, not a chemical reaction. Examples of this. If I take hydrochloric acid, HCl, and sodium hydroxide, NaOH, I put them together, I get HOH, which, by the way, is H2O. H2O is a molecular compound. So something did happen. I formed a liquid from two aqueous solutions. Therefore, it's a double displacement reaction. Another example. When lead nitrate and potassium chromate are mixed, see I have pouring them together, I will see this yellow precipitate forming. In that case, I have a solid forming. Okay, solid is your precipitate that forms. If a solid forms, it's a chemical change has taken place. The pattern we're looking for is AX plus BY goes to AY plus BX. The two positive ones switch places, or two negative ones switch places. But make sure when you're writing these out, you pay attention to those charges that you learned back in Chapter 5. I don't want to put a positive with a positive, okay? Potassium and lead both have positive charges. I would never write this as PBK, because that would be all positive charges. I have to pay attention to my positives and negatives. We will practice this in class using a worksheet and some practice problems that we will go through, but start thinking about the patterns that you have. If you have A plus B goes to AB. If you have AB goes to A plus B. These are patterns we want to look at. Make sure you have all the patterns written down. There should be 5 patterns. If you didn't catch those, go back and watch the video again. Find those patterns that we're looking for so we can identify these reactions and predict what reaction will take place.